Hey everyone, welcome back to my YouTube channel where I will be going through videos that cover math topics and different math subjects at school. So this is actually just following up on the previous video I made about calculus, where I mentioned that I would make another post about end behaviors of certain functions. So in that regards, there are some common end behaviors that you might see for functions. And so I'll go over those today. So the first really common one that you'll see are polynomials. A polynomial is any function such that all the exponents of x are positive whole numbers. So in this case, you could have a polynomial like a to the power a times x to the n, like so on until it gets to some constant, say for example 5. And where n has to be a whole number and it has to be positive because otherwise it will not work. So for example, a polynomial could be something like 3x squared plus 2x plus 4. That's a polynomial. But 3x to the half is not a polynomial because this exponent's not a whole number. Nor is 3x to the negative 1 because that's 3 over x. So in that regards, when you check the end behavior of a polynomial, you don't need to check any term except for this first term over here. So a would be the leading coefficient, while n would be the degree, so the highest exponent that's present in the polynomial. So there are 4 different end behaviors you can have for a polynomial, and those depend on whether n is odd or even, or whether a is positive or negative. So if a is positive and n is odd, you'll have a graph that looks something like this. So your limit of the polynomial as x approaches infinity is equal to infinity, and as this function approaches negative infinity, it's negative infinity. But if it's even, your graph would look something like this. It would look a bit like a parabola. A parabola is just an example of a polynomial with an even degree, and the end behavior is the same, whether the degree is 2, 4, 100, 1000, just any even number, unless of course the even number is 0, in which it would just be a straight line like this. But if this even number is not 0, then both of your infinite limits would actually be infinity, because the function starts from infinity, reaches its lowest point, and then increases again until it's infinity. So here both the end behaviors are infinite, and that's assuming this leading coefficient is greater than 0. But if it's less than 0, both of these basically just switch. So if n is odd, but the leading coefficient is less than 0, your graph would look like this. Think a cubic graph, but with negative at the beginning instead of positive. This positive example here is also like a cubic graph, but just a basic one. So if you compare it to this, the limits and end behavior are actually just the complete opposite as before. So instead of the limit of this function as x approaches infinity being infinity, it's negative infinity. And it's the opposite as you go to the other direction. Well, if it's even, just imagine that this function over here is flipped upside down. So it starts from negative infinity, reaches its highest point or the maximum, and then decreases to a negative infinity again. So you would have both of your limits as negative infinity. And I should have left myself more space when writing this, but it doesn't matter because the basic limits are over here. Another type of common end behavior that you'll see are rational functions. And I'm only looking at the the limits of these rational functions as x approaches infinity and negative infinity. A rational function is just any function which has a polynomial over another polynomial. So it is possible to have vertical asymptotes, but they have no effect on the end behavior of it. Again, like what you did with polynomials, only look at the first term of the numerator and denominator. A and P represent leading coefficients, while M and N represent the degrees of the numerator and denominator. So, like with polynomials, you'll also need to compare the degrees and the leading coefficients. So if M is greater than N, so if this numerator's degree is greater than the denominator's degree, it's either going to go to infinity or negative infinity, in which you just divide the leading term of the numerator by the leading term of the denominator and use the polynomial limits above to find the end behavior of it. And I'm just writing this on the screen for future reference. And that's only if the degree of the numerator is greater than the degree of the denominator. Again, these have to be polynomials for this to apply. Because if this is -1, then a negative degree in the denominator would kind of move it up a bit. So it would just end up increasing further. While if M and N have the same degree, then you would just divide A and P. So the result of dividing A and P, say A is 2 and B is 3, divide 2 by 3, and that's your end behavior. But that's only if these two degrees are equal. So your end behavior of this function, if the two degrees are equal, would just be the quotient of your leading coefficients. So numerator divided by denominator. And that doesn't matter whether it's positive or negative. It makes no difference at all. But if the denominator's degree is greater than the numerator's degree, that just means that the denominator will increase faster than the numerator. So this function actually just keeps getting smaller and smaller until it reaches 0. So both limits in this case, if the denominator's degree is greater than the numerator's degree, would just be equal to 0. And that doesn't get affected by the leading coefficients or anything. It's just 0, no matter what. So that's rational functions. And now moving on to exponential functions, your basic exponential graph would look something like this. So it starts off really small, actually very close to the x-axis, so the negative, like the limit of this function as x approaches negative infinity is actually just 0, because if you take the basic form of any exponential, we'll take e to the x, but the base doesn't really matter as long as it's positive. As this number keeps getting smaller, e to the negative x is just 1 over e to the x. So the denominator just keeps getting bigger. So as this keeps getting bigger, the overall function keeps getting smaller until it reaches 0. But after 0, it just keeps increasing. It doesn't stop decreasing. So the function is just going to keep getting bigger and bigger. So as x approaches infinity, this function will also just approach infinity. But if instead of e to the x, you were to have e to the negative x, then your end behavior would just switch. So instead of the function approaching infinity, it would approach 0. So this would be e to the negative x, and this is e to the x. This is called a This is reflecting across the horizontal. No, this is reflecting across the vertical axis. My bad. And just forget about this drawing. It's definitely not the scale. So back on topic, the limits just switch. If instead of the exponent being positive x, it's negative x. So you have 0 as x approaches infinity, and infinity as x approaches negative infinity. But if you were to add a coefficient over here that is negative, instead of this being infinity, that's just negative. It doesn't change anything. It doesn't change the limit where the function approaches 0, but instead of it approaching infinity, it will approach negative infinity. And that doesn't matter whether this is the infinite or negative infinite limit. So, for example, a function that this would be the function negative e to the x. As you can see, the n limit as x approaches negative infinity is the same, but instead of going positive, it's just going more negative. Well, a log function is actually just the inverse of an exponential function, but a log function isn't actually defined on all real numbers. The basic log function is only defined from 0 to infinity. So if f of x is equal to ln x, this is the natural log, so log base e. And this is what you'll also use the most in calculus, then your infinite limits or your end behavior wouldn't even be infinite in one of the cases. One end of the domain is actually just 0. So as the function approaches the y-axis, so as x approaches 0, the function just keeps getting smaller and smaller, and actually just keeps getting closer to negative infinity. It just goes further down. So as the natural log of x approaches 0, your limit would just be negative infinity. But as it approaches infinity, your limit here would also be infinity. And this also changes if you have any coefficients over here. Like if this is a negative number, then instead of negative infinity, it would be infinity and negative infinity. They would switch. While if you were to have negative x instead of x, then the graph would just be flipped across the y-axis and look something like this. So a negative can actually have a very big impact on the end behavior. And now to trig. See, the trig functions actually have a very peculiar end behavior, in the sense they don't have one. These functions just keep repeating over and over again. So it's impossible to know where it truly ends. It just keeps oscillating between -1 and 1. So how do we know where it ends? We don't. So the limit of any trig function as x approaches infinity or as x approaches negative infinity doesn't exist. This isn't exactly the case for inverse trig, well, at least for the arctangent function in inverse trig, but we'll get into that as we look at more inverse trig functions later on. Thank you for watching and stay tuned for the next video.